Hello, and welcome to Creating the Next Generation of Designers and Manufacturers with Additive Manufacturing. I'm David Manti, Executive Editor of Product Design and Development. Joining us today is Dr. Christopher Williams, Director of the Dreams Lab at Virginia Tech, and Bruce Bradshaw, Director of Marketing for Stratasys North America. A couple of housekeeping items first. I'd like to direct you to ask questions for the Q&A portion of the presentation in the Question and Answer tab. Also, the presentation is available to download at the folder icon at the bottom of your screen. I'd like to now turn it over to Dr. Christopher Williams.
Great. Thanks so much, David. Again, my name is Christopher Williams. I'm an assistant professor here at Virginia Tech in the Department of Mechanical Engineering and the Department of Engineering Education. I want to thank Stratasys and Product Design and Development for the opportunity to speak to everyone today. Really what I want to do today is share with you some of the work that we're doing here at Virginia Tech with additive manufacturing, but more importantly, share with you some of the case studies that have come out of all the great work that myself and my colleagues have been working on using additive manufacturing in a lot of different use cases that we hope will be of interest to all of you, whether or not you're in industry or in academia. So what I want to begin with today, before we really begin with these use cases, is to make sure we're all on the same playing field here about what we mean by additive manufacturing. And notice that I'll use the word additive manufacturing instead of the word 3D printing. Additive manufacturing is the ASTM standard terminology referring to this class of technologies that build parts from layer by layer from the bottom up. And this is really to sort of contrast it against something like subtractive manufacturing like CNC, or where we're removing material to make products. So in all additive manufacturing technologies, we all start with a CAD model, a solid object, and we end up with the actual object in physical representation. And the way that's done is it's first exported to a standardized file format, like an MP3 or a PDF. Our standardized file format is the STL file. And then we pass that on to the machines themselves, where they are sliced layer by cross sections. And then each slice is passed to the printer to actually create the first slice, the bottom slice, and then to build on that slice layer by layer until the part is complete. In effect, the actual original idea came from these topology maps, where we had a challenge, which was how do you create a 3D object, and the way it can be done is by representing it by a bunch of stacked layers. Now, again, there's a lot of different technologies on the market that all fall underneath this umbrella of additive manufacturing, and the really only thing that differentiates them is the way in which they create each layer, but they all create the first layer at the bottom and then build upon that layer by layer from the bottom up. So one way, probably the one that you're most familiar with, is fused deposition modeling, first patented by Stratasys. And in that process, the way it creates a layer is actually through what we sometimes refer to as a robotic hot glue gun. Basically, it's a thermoplastic filament that's being extruded selectively. There's a filament being fed through counter-rotating wheels. It's being molten and then drawn to draw that one layer. And then on an elevator, that elevator lowers, we draw the next layer, and we continue from the bottom to the top. In the Stratasys technology, you'll see they have two different extrusion heads. One that actually allows it to create the build material. Here in this diagram, that's the white lettering of the word dreams. And then it also has a support material. That's the brown material. And that support material is actually sacrificial. It's there only to help create complex geometries, basically difficult overhangs and undercuts if you're doing a subtractive technology. This is a sacrificial material. It's water soluble underneath the Stratasys platform, which allows us to make some really complex and shapes that really can't be made by any other means. Now, another technology that, again, is an additive manufacturing technology is the Stratasys PolyJet 3D printing technology. And again, same idea. We take a model, we slice it, we build it layer by layer from the bottom to the top. But instead of extruding a molten thermoplastic, in this case, the technology is actually inkjet printing a photopolymer. Now, a photopolymer is a liquid resin that actually can turn solid when it's exposed to UV light. And in the PolyJet printing process, they actually have inkjet print heads. So imagine your 2D desktop printer. Instead of printing ink, it's now actually printing this photopolymer resin. And as it passes, it actually can jet almost about a 2 to 3 inch section of each layer at a time. So it's a very fast process. And as that print head passes back and forth, the mounted UV lamps actually cure or solidify that jetted resin. So again, layer by layer, you can create parts from the bottom up. Now, in the top-of-the-line object connex models, you can actually make multiple materials, which is a very unique feature. It's the only commercially available technology that will allow you to do multiple materials. So we actually have 3 different types of print heads, one that does the sacrificial support to, again, allow complex geometries. Then we have 2 other print heads that can mix many different materials, which will demonstrate some of those applications here. So what really gets us excited about additive manufacturing? Sure, it's digital, and sure, it allows us to email files and do more domestic, fabrication, and makes fabrication much quicker and faster and a little bit easier to do. What really gets us excited in our lab here at Virginia Tech is the complexity, because it really transforms how things can be designed. So when I give talks on additive manufacturing, I always show this slide. What we show here is on the left is an actual 3D printed or manufactured part, and on the right-hand side is an image of a single layer of that part. Now what you see actually are 2 different images on the right. You see one where the part is being printed on its back, and one where it's being printed on the side. Again, in additive manufacturing, orientation doesn't matter. The fixturing is not a problem, so we can actually print in any orientation. So what you see are actually 2 layer representations of that same part. So on one image, it's just a bunch of this cellular sort of matrix. If you look at it's printed on its side, it's a bunch of horizontal lines. So I always ask people, do you think you can make this by traditional means? Could you machine that? Could you injection mold that? And most people say, sure, we could probably do that. We might be able to get, might not be able to get those vertices to be so, acute, but we probably could do that. So then I show them this next part. Could you manufacture that with traditional technologies? Again, this is like a serpentine kind of honeycomb shape that's swept like in an S. And to our additive manufacturing process, each layer just looks like a bunch of curvy lines. If I fabricate it on its end, it's just a sort of a grid that sort of shifts left and right to make this stacked honeycomb swept approach. Now this, I would say, is impossible to manufacture traditionally. Maybe you can extrude it with a very careful pull, but there's no way to machine that or injection mold that. And some people maybe argue with that, but what about this? This is what we call a cellular material, a structure that is very lightweight, but yet very stiff. It's a material that we see in nature, like in wood, bone, or coral. It's a naturally sort of optimized structure. And these are the kinds of structures that we as engineers would like to take advantage of, but there's really no way to manufacture them until now with additive. So again, what you see on the left is actually an object that's actually printed on an object connex. And on the right, I'm going to start an animation that shows you every 5th layer of the layers. So again, traditionally, there's no way to injection mold that. There's no way to machine that. There's no way to cast that. To our printer, though, it's just a series of dots that just sort of move, and they're stacked on top of one another, and they basically grow into these truss-like structures. So in our lab, we sort of have this tongue-in-cheek field of dreams reference, which is, if you can design it, we can make it, which actually points to a really important point about additive manufacturing. Manufacturing has traditionally been sort of the roadblock to realizing new ideas, because it's always about manufacturing constraints. In additive manufacturing, those constraints are almost completely gone. So now the challenge and the real roadblock is just conceiving of the design and also being able to create your ideas in a CAD program. And so that's sort of the focus of the work that we do at Virginia Tech in what we call the Dreams Lab. And you can see at the Dreams Lab we have quite an array of technologies, both the Stratasys technologies as well as other additive manufacturing technologies that allow us to process lots of different materials. So we really work across the entire spectrum of the different technologies. And our clear, our key mission here is really to work on the basic sciences of additive as well as the pedagogy, which is all about training engineers to learn how to use these technologies to make them to be viable platforms for making real products. And the DREAMS acronym, I promise, was done afterwards. It was not done with any kind of foresight, but really it was because we wanted to focus on the 3 things that we thought we would do fairly well. And those are the areas of design, research, and education. So in the areas of design, what we look at are these methodologies for what we call DFAM, there's no Mark's handbook for additive manufacturing. There's no guidebook, like there is for injection molding and other types of manufacturing. And so we want to help propagate those kinds of methodologies. We also want to focus on these cellular materials, this really unique set of class of geometries that just can't be made by any other means. I should mention that in that photo on the right, you'll actually see that half of that product is black and half of it's white. That's actually the Vero white, which is a very stiff polymer from the object connex, and the black is actually this tango black material, which is elastic, almost elastomeric. So what we've done is we actually not only have a complete complex geometry, but we actually have modified its material properties on the fly. So as a designer, I not only can specify where the material is, exactly where I need it, but I can also start specifying exactly the material properties where I need them, which is something that we as designers have never had that opportunity to do before. In the areas of process and materials research, we do a lot of work in metals and ceramics. We're also working with the object connex process to look at embedding electrical systems and actuation systems. So again, here on the right, you'll see some images from a paper that we published, or we're actually printing what we call almost like robotic systems that we've embedded fibers in that you can then, using that mixture of flexible material and stiff material, we can actually make appendages that actually can move. That entire part was made at one time using the object process through an embedding procedure that we developed. So that's no assembly at all after that process. We're also doing some work in some nanomaterials work. These are images where we're actually embedding, so sort of what we call printing invisible ink, where we're using an object VeroClear process and putting some unique quantum dots in the material, perhaps for part tagging in the future. And then, of course, we have a big focus on education, which is what we're going to talk about today. This is really all I'll talk about our basic research, and you're welcome to contact me afterwards if you have any questions about these kinds of projects. But really what I want to focus on today is this question: what does the future designer look like, especially within the context of additive manufacturing? And traditionally, design and manufacturing have always been separated by this wall, if you will. And in the past, design looked like the designer creating problem requirements, generating CAD models, having some models of some sort, and then sort of throwing them over to the wall to the manufacturer and say, I hope you can make this, because it's been optimized. The manufacturer checks against material properties, process capabilities, and says, I don't think so. Let's try that again. And it's a very iterative process. Now, these are the old days, admittedly. And so we do the thing what we call now is concurrent engineering, right, where we set our designer next door to our manufacturer, and they still do this iterative cycle, but perhaps a bit quicker, and hopefully concurrently. But that's not really what we think the future designer will look like. What we really want to do is create a new engineer, one that is both the designer and the manufacturer, an engineer that knows both the problem, is able to frame problems and model problems within the context of what is possible with manufacturing. Now, this is something we've always wanted to do, but it's always been challenging. How can one person have so much knowledge, have such a breadth of knowledge? And the answer actually might be is because of additive manufacturing, because this is a technology where the designer is the manufacturer and the manufacturer is the designer. And to truly take advantage of what these technologies are capable of doing, you've got to know what the additive manufacturing technologies can and can't do. And so this is all sort of under the umbrella of what we say is design for additive manufacturing. And this is something that we at Virginia Tech are really working on and educating our students. And this slide shows a lot of different case studies ranging from aircraft ductwork, which is the top left, that are flying. It's a representative image of actual objects that have been printed and are flying on military aircraft. Hip implants. This is a study on the right there, the upper right, of some students in the UK who have created an entire UAV from additive manufacturing. The bottom left and bottom right images are probably our most common industrial case studies of hearing aid shells that are custom made or custom braces by Invisalign. And in the bottom middle there is Scott Summit, an industrial designer who's designing custom prosthetics that actually have an aesthetic and also have some functionality. And all of these cases, they were realized because the designer knew what the processes were capable of doing and were able to design to them. And this is really where the power of additive manufacturing comes in. At Virginia Tech, we do this. We actually have integrated additive manufacturing across our entire curriculum, all the way from the freshman engineering program all the way down to the bottom there, where we actually have a dedicated undergraduate, graduate level course in additive manufacturing. And just quickly to focus on that, we have, we actually wrote a paper about that course with my colleague at the University of Texas, and we have specific learning objectives where we want the students who leave are able to think about all the technologies and be able to design within their capabilities and limitations. They're able to evaluate and select these technologies. They're able to look at the fundamental causes of errors and irregularities, just like in any other manufacturing process. And they can then actually apply these techniques to design a brand new product that's been specialized for these technologies. And actually what we're going to show today is some of the projects that have come about from this class, as well as all the other types of work that we've done with all of my colleagues across Virginia Tech. So let's get started with that. What we're going to do is I've segmented all of this in sort of the spectrum of uses of additive manufacturing, ranging all the way from originally what we called rapid prototyping, which is prototyping components before we go to quote-unquote real manufacturing. And then we then move up the scale a bit to tooling, where we actually are printing objects to help us set as tools or molds for traditional manufacturing. And then finally, where we really want to be headed, which is using these technologies to manufacture end-use products, products that come off the printer and go straight on to the end-use scenario. So let's start with the prototyping. And this is really where the technology all started, actually. Stratasys, with their FDM process, was one of the leaders back in the early 90s when all this technology first kicked off, and was for these types of applications. This comes from a second-year design course at Virginia Tech. Here we had some students who had this interesting idea of, hey, I've got all these keys in my pocket. How can I get rid of that discomfort? Let's make it like a, Swiss Army knife, right? So they have this, napkin sketch idea. They go to CAD. They make this a beautiful, CAD model. They design modularity into it. I can snap on images and make it a beautiful thing. They won Best in Show, and as a result, they got to print their object. And it wasn't until they printed their object that they realized that this 4 inches that was on the computer screen that they measured actually wasn't so comfortable to stick in their front jeans pocket. And it wasn't until they actually held it in their hands that they realized, hey, this needs some redesign. And this is, again, is a traditional, very, broad type of use for this technologies. And we do this quite a bit in our freshman and sophomore and senior levels. We also use the technology to support student design projects. This is an example from a colleague of mine, Michael Gregg, in the Department of Engineering Education. He has his first-year engineers learn, actually get to apply what they've learned about CAD by designing a Rube Goldberg device. Each student team is given a certain space in which they can work, and their goal is to maneuver a marble from one corner of their cube to the other by doing with a special trick in between. And at the end, he can stack all of these up and make this tower, and he's got this 3D printed display piece. And really, in this case, what the printing is being used for is all about getting students to actually integrate and learn about and actually put to use what they've learned about CAD. And this was all done, I should mention, on an FDM Stratasys U-print machine. So these are sort of smaller scale, desktop scale machines. Another use case here is from a senior design team in the Aerospace and Ocean Engineering Department at Virginia Tech. In our AOE 3D printing lab, we've got 2 Objet 30s. And here's an example from our human-powered submarine team. This is a team that has to create a submarine that is completely human-powered, and they have to design and build this thing from scratch from the bottom up every year. And here's a sample part that was actually, again, printed, and they use an object here. This is actually, it houses a steering device, a steering column, if you will, and it was designed and it's been used by Object. It's got a great surface finish and allowed them to put their logos and make a nice, product there. But the aerospace team actually does a lot of wind tunnel models. So again, here you've got these, very complex curves, very complex airfoils that have to be perfectly represented for these, precise wind tunnel models and testing. And they needed a way to quickly fabricate these. These are something that would take a CNC machinist quite some time to do with such a complex curve. But for the digital fabrication capabilities of Objet, this is not a challenge. And they, again, did use an objet because an objet process has got one of the best surface finishes of any of the additive manufacturing processes on the market, and so that's something that they were able to do quite easily, and they do a lot of work with that. I should also mention that they're investigating looking at larger wind tunnel specimens, I'm talking 6-foot sections, in which case they would actually, and they're actually looking at doing supersonic kind of testing, where you might need a higher temperature material. So they were looking at an FDM sort of ULTIM-like material for that process. Another example of a senior design project comes in the form of some work by our Center for Energy Harvesting Materials and Systems, led by Dr. Shashank Priya. This is a student project. They were looking at making a portable wind turbine, a windmill, if you will. This whole device actually fits within the scale of almost a soda can, which actually is the base itself. And this is a windmill that actually was created on an FDM machine. Again, very easy way to make these complex airfoils that have to be, again, have been optimized to catch as much energy from the wind as possible. And again, a really unique product concept that there was really, before we had additive manufacturing in our labs at Virginia Tech, there was really no way to make that project a reality. The same lab actually had a master's student who completed what they called the DART hand. It's a robotic hand that actually you can see on YouTube and actually in the papers, actually can type on a keyboard. And actually in this case, they're actually trying to make a robotic hand to simulate a human hand for the purposes of making like a robotic patient. So they're actually trying to make it a full human patient that for doctors to be able to do testing and learning situations. So again, that's all been made on an FDM component, and it's a really, again, very quick way to make parts that are lightweight and are specialized for robotic purposes. Traditionally, they'd have to machine that out of aluminum, and it would be very time-intensive, would waste a lot of material, and don't really allow themselves for quick iteration. Another really unique application is out of a class that we have in microrobotics. This is a small-scale robotic inchworm. And this, again, required an additive manufacturing process that had a very high resolution. And actually, it's got these small little rubber feet. So this required a process that actually had a digital material, or the ability to make multiple materials. So this small robot actually has both the white parts of the stiff pieces of the robot. It has functional shape memory alloys inside of it, and actually these little rubber feet actually allow it to move. And I will invite you at this time to click on the See It in Motion link. If you click on that link right there where it says See It in Motion, it will open in a new window a YouTube link, which will actually allow you to see this small inchworm in motion. So this is just done with shape memory alloys. And you'll see that actually the VT logo on that little inchworm is printed in Tango Black. So this is a case where sometimes we use mixed materials for aesthetic purposes and not for functional purposes. But on the bottom, they have those small little nubs that allow it to move and grip the surface. So I'll invite you to switch back to your tab to come back to the presentation, and we'll go on to the next case study. The next case study is sort of in this realm of what we call biomimicry, which is looking to biology to make mechanical systems. This is something that's a big focus of a lot of researchers here at Virginia Tech. And we have a great professor named Rolf Mueller whose specialty is in bats. And he actually looked at horseshoe bats, a special species that's only found in China. And what's interesting about this horseshoe bat is he's trying to look at its large nose and ears to actually try to develop a mechanical sort of representation of that to create a more efficient sonar. So what he looked at is he actually can take horseshoe bat specimens from China and actually have them CT scanned. They then email him those CT scans. And then from that CT scan, he can actually create 3D models, digital models of those bat ears. And then he came to us and said, well, can we make this? And I said, not only can we make those, but we can actually make them in a material that is very similar to the bat's ear, which has a sort of leathery, flexible kind of membrane. But with the Objet Tango Black Plus material, we're able to recreate a not only the bat ear, but actually out of a material that's very flexible and represents sort of what the bat's ear can look like. So Rolf is now able to actually put that ear onto his test stand and do acoustics testings with a geometry that comes straight out of a biological sample. We similarly had some students who actually were looking at human elbows, looking at, again, sort of robotic applications, and they wanted to replicate the ligaments and tendons and cartilage and also of the human elbow as well as its stiff bones. And so they were able to actually create a model of that using, again, the mixed materials process. And we're going to, for the sake of time, we're going to go ahead and skip this video, but you can check it out some other time if you'd like. It's actually in the promo video from Virginia Tech. Along the same lines of biomimicry, is this, what is this? And I'll invite you to click on this link. What is this link? I'll go ahead and invite you to click on that on YouTube. And what you see here is a good friend of mine, Jake Soha, who actually studies this stuff called flying snakes. It's actually probably my worst nightmare. What you're seeing is a snake actually leaping off of a test stand, and its body takes the form of an airfoil and actually can glide in midair. So here's a snake that can actually fall with style, if you will. And Jake's looking at studying these. How do these biological specimens, what's the shape of their body such that they can glide, if you will, and how can be so efficient? So we'll invite you to come back to the presentation. And actually, at the next slide, you're going to see an image of Jake sort of pointing at this model of the snake that we 3D printed for him using the object Connex. And again, I will invite you to click on the what is this link. And you're going to have Jake explain to you exactly how he used this technology. So what you heard from Jake was the ability, again, to manufacture these really interesting parts that just can't be made by any other means for his wind tunnel tests. So we're going to move on now to the next portion, which is all about tooling. So we've been talking about prototyping. Let's talk a little bit about tooling. And one thing that we can use very easily is in the process of vacuum forming. In vacuum forming, obviously, we have to have a mold in which we form plastic sheets to create plastic components. And a good friend of mine, Dr. Dennis Hong, who runs the Romello Lab, he likes to work on soccer-playing robots. And what Dennis works on is he needed a chest plate for one of his robots, so we were able to use an FDM machine to actually print the chest plate of his robot, and then it turned a robot on the left to the robot on the right, made it much more aesthetically pleasing. We did this with FDM material. You can also do it with a high-temperature object material, and it's a very quick and easy way to make high-quality molds for vacuum forming. Similarly, we can do the same thing in sand casting, and in sand casting we can print directly patterns that we can then embed into foundry sand. So again, we tend to use the object process here because of its high surface finish, its high quality surface finish, and its high resolution. We're able to make some very small lettering, which translate very nicely into sand. So we have a foundry here at Virginia Tech, which allows us to teach about foundry engineering, and also allows us to explore new technologies like 3D printing in foundry industry. So we can pour our aluminum straight into that sand, break the sand mold apart, and of course, now we have an aluminum piece that we originally started by digitally creating that out of polymer. We also do some work in investment casting using three-dimensional technologies where, again, we print our master patterns. And in this case, we're actually printing our statue of our mascot, the Hokey Bird. And so since we wanted so many of these, we printed one master pattern, then put it into a polyurethane mold, and then we did wax patterns from that. That then allows us to do traditional investment casting procedures where we coat that wax pattern in a ceramic shell, melt away the wax in a furnace cycle, and then pour in a metal, in this case aluminum, to actually make aluminum replicas of our part. And again, traditionally, this would have required us to CNC machine a steel, or excuse me, some other type of master pattern out of a metal or some wood, perhaps. In this case, it's all been designed digitally. Actually, in this case, we actually started with a 3D scan of a 2-foot-tall statue, then reduced its size, and then printed it all within the span of about a day. And then we had our master pattern, and we're ready to start making our statuettes here. But in cases where we don't want to make lots and lots of copies, we look to a different way of making a pattern. Here we're going to the FDM process to make a pattern that we don't go to wax. We actually work straight from the product that came out of the printer. So this is an ABS plastic pattern. This is a truss structure, again, a sort of cellular material, something, again, that can't be made by any other means. And we actually cast that, we take that ABS pattern and we directly coat it in sand. And of course, I should mention, there's no way to actually make the wax replica of that because we couldn't have done that in a polyurethane mold. So we take the ABS pattern, put ceramic around that, burn away the ABS, and then we're left with our aluminum piece. And we've written papers about this, and I know there's been case studies of other FDM parts as well that used for investment casting purposes. Another type of casting is a thing called polymer casting. And I'll invite you to click on this link, the See It in Action link, to learn about a robotic jellyfish application here at Virginia Tech. So you might ask yourself, how in the heck do they make that? So I'll invite you to come back to our presentation. And the way in which they made that, again, that was a silicon sort of jellyfish with embedded shape memory actuation. And the way in which that was done actually was through 3D printing. So using an FDM printer, we actually printed a shell in which we can then cast this silicon material into. So they were able to, again, digitally design and then fabricate using FDM that mold. They then lay in their shape memory alloy and the spring steel there, and then they then close that mold and cast the device. So I'd like to conclude the presentation today with a discussion a little bit about how we can use these technologies to go all the way to end-use manufacturing. And that's really what additive manufacturing is all about. And I'll use the case study of some of our students in the Formula SAE competition. This is a competition where students are asked to design and build from scratch every year a small-scale Formula One race car. This is a project by a student of mine who actually wanted to make directly his intake manifold to the engine. So he had this design which had tapered runners to provide equal airflow to all cylinder heads. It had a tapered plenum. It was a design that just couldn't be manufactured with traditional aluminum extrusion and welding. So he had designed the product. He'd gone to CFD, computational fluid dynamics, to prove that his design was ideal and was something that was worth exploring. And he did iteration work, and then he directly printed that intake manifold. Now, at the time, this is actually my first semester here at Virginia Tech, we were working just with ABS, and it's just a little too hot on the engine to put a direct polymer part, obviously. So to solve that problem, we actually reinforced that part with a high-temperature epoxy and did a carbon fiber layup, which gave it not only the strength it needed, but also the temperature resistance to actually be installed directly onto the car and run with no problems. Now our team is actually working with Stratasys and the Ultim material, very high temperature material, that they can actually directly fabricate their intake manifold and requiring no post-processing, so no epoxy infusion, no carbon fiber layup, and directly print and then install that intake manifold. Not only that, but they've actually designed a way so that it's a modular platform. They can actually say have the two sort of dome-shaped ends. They put different spacers in between to explore how the different volumes of the intake manifold affect their efficiencies. So up on the left here is the car itself, and on the bottom right you'll actually see, this thing is, it's pretty hot on the engine, right? So in this material, this polymer material survives quite nicely. So that's direct off the machine and straight onto the vehicle. Another application we're exploring with the team this year is in the area of a custom-fit steering wheel. So we have a student who actually put modeling clay on the steering wheel and then put his hands on there and got to the form at which he was most comfortable with. We can then 3D scan that mold and then design it such that it can be printed and then installed on the existing steering wheel platform, and then we can directly fabricate that. And this machine we actually chose an object process, and this is the first iteration. We're just making sure it all came together. The next iteration will actually have a coating of the elastomeric-like material to provide some of that sort of squishy feedback. So here it is in his hands, completed product. Again, straight off the machine, straight onto the car. Another quick application we have is in the area of autonomous vehicles. We have a small-scale system that is completely autonomously controlled, and its biggest challenge is it tends to run into things while it's being optimized in its control system. So that aluminum bumper, which has always been hogged out of aluminum, with CNC machining, kept having to be repaired, and that was about a 2-day turnaround time. So the students came to me and said, well, can't we just print this out of plastic? And I said, well, obviously you designed this for aluminum and not, ABS, so we need to think about redesigning the structure. So polymer, sometimes people get afraid of and say, well, that's not a real engineering solution. But actually, the solution comes through the design. You can redesign the object knowing that you can place material anywhere you want to get equivalent performance for also equivalent mass. And that's something that, again, it all comes down to being able to navigate both the design space and thinking about the opportunities that exist with additive that just haven't existed in the past. Finally, I'd like to share with you some sample projects from my students' class where they had to look at additive manufacturing and think about brand new products that were designed specifically for use of additive. So here's a set of students who designed a wine venturi. This is using the object transparent material, and this is printed as one single piece. And inside is this complex double helix curve that actually aerates the wine, makes it nice aesthetically pleasing, and gives you a nice glass of wine, I'm told. Another product that my students designed was the idea of a handheld 3D campus mat. In this case, they, again, use the object Connex and its multiple material capabilities to have some different features to actually label buildings and roads and parking lots. The idea being that you could carry this map around on tour guides to actually have students have a campus map. And you can actually see, printed doors and throughways for, the various tunnels that we have in between buildings. Another product, of course, is your custom phone case. And here, again, students specifically use the object technology and multi-materials to include both stiff components for protection, some black rubber texturing for grips. These corners provide some, shock absorption, and also has a kickstand. So you'll see some sort of black piece that you can, it's actually hinged. The whole thing assembly has been printed as one piece. And then finally, we'll show you this project, the idea that you could actually print custom earphone adapters for you. So they actually molded a customer's ear, 3D scanned that ear mold, and then again, directly printed that such that it could fit just that custom ear. And again, that was made out of the Tango black material. So this sort of concludes a long, different, quick-fire approach to all these different technologies. You'll see they're very diverse applications, and they range all the way from prototyping to tooling to manufacturing. And I just want to close with one last example, and this is one that means a lot to us. We've got a great student here whose goal is to become the first blind astronaut, and her goal is, it's a bit challenging, right? How do you make it through multivariable calculus when you can't see three-dimensional geometries? And so with that in mind, we actually worked with the math department, and we developed an algorithm that took these mathematical functions and actually made them to be printable objects. And I'll invite you to click on this last link, which will send you to a YouTube video of the students' first interaction with these 3D printed mathematical models. And we'll sort of end the video. The point here being is not to necessarily give you a tutorial about a reminder of your multivariable calculus class, but instead to show you that this technology has got such a wide array of applications, all the way from making components for automobiles to educating folks in new and interesting and innovative ways. So with that, I'll invite you to come back to our presentation, and right here you'll see some of my contact information. There's also a link embedded in that to actually see an overview of our lab. But with that, I'll conclude and pass it on to Bruce.
Awesome presentation, Chris. Thanks a lot. Fantastic. Folks, I'll come back to that slide as well when we get to the Q&A section, so you have Chris's contact information later on. I'm just going to take just literally 5 minutes and give folks a background on Stratasys and a little bit about our product lineup and a little background on the company itself. As Chris referenced, he uses two different technologies. One he referred to as Objet, and the other he referred to as FDM. FDM is the technology that was developed by Stratasys, and the PolyJet technology was developed by a company by the name of Objet, and we've actually recently merged with Stratasys. That was back in the December timeframe. So as the two companies merged, we have really the largest 3D printer manufacturer in the world now, with offices all over the world, a workforce of over 1,100 employees. Again, revenues of almost $360 million. I won't go through all the different bullet points, but you can tell there's a lot of horsepower behind the development of the 3D printing technology. This next slide I just put up because I'm sure there's representatives of lots of industries. Chris talked about medical applications. He talked about aerospace applications. He talked about education applications. Just looking at these logos, I'm sure folks on the presentation can identify with one, two, or many of these logos here of companies that are actually utilizing Stratasys 3D printing technology to advance their product development. Next, we didn't work with Chris, but as he was going through his presentation, I had to laugh because we have 21 different products in our lineup now as a combined company. So we tried to put some logic and thought behind the product line so that folks, as they start to come in and introduce themselves to 3D printers, depending on where they decided their needs were and their fit was, they could easily direct themselves to a segment of our product line. And it's interesting, you'll see the products on the left. We have something called the Idea Series, and as Chris pointed out, he referenced an application of building some set of keys or a key holder, and he talked about it being an idea and the thought of it being on a napkin originally. The products in this category, our Mojo and Uprint line, are actually geared towards that type of a person or engineering department where you have thoughts and ideas and you want to be able to produce something quickly, but you don't have a huge budget necessarily to invest in 3D printing, but you see the value in it. And as Chris referenced, the students that were designing that keychain didn't think about, wow, this doesn't fit in my pocket. And we use a term here a lot. A picture is worth 1,000 words. A part is worth 1,000 pictures. And his example underscores that immensely. And this product line, the Idea Series, allows folks to get into 3D printing without a huge investment, but reap the benefit pretty quickly. The next one is the prototyping, or our Design Series. And again, Chris referenced lots of examples in there, and we have that's where the majority of Objet products reside. There were some questions, and we'll get to them momentarily, about resolution and different materials, and we'll talk about those in the Q&A section. But the Objet product line and a few of the FDM products reside in this design series. And again, it's for folks that are actually doing more advanced designs than a concept model. And finally, there's the production series. And again, Chris referenced actually utilizing Ultem material and other ABS materials in a production way where they're actually producing real parts. And the Fortis product line falls into this category, the majority of it. And again, the thought here is to bring some logic to our product line. So depending on what your needs are, you can actually look to one of these and kind of earmark yourself towards one of those. 2 more slides on my section, and then we'll go to Q&A. Chris referenced lots of different materials, and the combined company, we now have something like over 120 different materials available for different purposes. We have biomedical material, we have ABS-like material, we have polycarbonate material, we have rubber-like material. There's a whole laundry list of materials. And the thought behind this is, if you're designing a product, you're trying to replicate the end product as best you can. And the more materials you have at your disposal, the easier that's going to be. Or if you're in a production environment and you need a polycarbonate material or a high-temp material, you're in aerospace, you need to be able to produce that end part with a material that can withstand the rigors of real life. And we have that material as well. Clearly, there's 4,000 engineering plastics out there, so there's a long way to go between where we are now and the number of engineering materials. But I can tell you that Stratasys, the investment in material development and what materials we have to serve the 3D printing world, far and away is better than the competition, and we have a huge investment in material capabilities, and so we'll be obviously adding to our portfolio of materials as we go. And I won't spend a lot of time on this. This was, Chris referenced this earlier, which is the 2 different technologies that we have. One is PolyJet and one is FDM, and he did a great job of explaining it, so I won't take a lot of time or any time with this. The only thing that I will stress is, as Chris referenced, the PolyJet side, we have a technology called Conics that allows us to blend 2 materials. And the only thing I'll say about that over and above what Chris had mentioned is it's not taking 2 materials and jetting them and they blend in midair as they hit the tray. It's actually a very scientific way of laying down the dots. In the 3D printing world, they're referred to as voxels. People know them as pixels in the 2D world, but they're voxels in the 3D printing world. And to get a desired mechanical property, we scientifically lay down 3 dots of a rubber-like material surrounding a rigid-like material to get a specific, repeatable mechanical property. So it's a very scientific way of doing it, and it allows you to get repeatable results over and over again. So that's really the extent of my presentation. I'm going to go back a few slides here to put Chris's contact information back up there for folks. And with that, David, I'm going to turn it over to you for Q&A so that we can answer questions for folks. I know there's been a few in the queue already.
Thank you, Bruce, and absolutely very interesting presentation, Dr. Williams. I appreciate it. First question comes from Bartholomew. What technologies offer the best resolution, material strength, and cost?
I'd be happy to take a crack at that, Chris, but before I do, I'd love to get your unbiased view of it. You have multiple technologies, including Stratasys technologies, but also competitive technology, and so I'm quite confident that you'll answer it in a very unbiased way.
Sure. So basically, the answer, unfortunately, it's a typical engineering answer, is that it all depends. There's no something we always push to the students. There's not yet a panacea. There's no such thing as a 3D printer that will hit all of your requirements. So the key metrics you've identified, Stratasys' FDM definitely tends to be the best as far as cost. It offers some pretty good, robust parts, but its resolution is where the object technology definitely is superior. And when it comes to mechanical properties, the laser sintering nylon process is very nice, but it also has some challenges with cost as well as being able to operate in an office environment. So You notice that in the additive manufacturing class that we teach, we really focus a lot on technology selection, and there really is not a one-size-fits-all technology. That's the honest. I know that's sort of perhaps a cop-out, but that is the truth. It's all about finding your application, and it always tends to come down to materials, is what and cost. So we tend to make decisions based on those.
And I'll just add to what you said, Kristen, and it's actually one of the things that drove Objet and Stratasys to merge. We recognize exactly that there are multiple technologies. It's just like a carpenter has multiple tools in his tool bag for different reasons, and it's the same for 3D printers. And clearly, we feel at Stratasys we cover a large spectrum of that. But there are some competitive technologies like metals. For instance, we don't print metals, and SLS laser sintering does have that as a technology. So depending on what your needs are and what you're doing, you need a different 3D printer or additive manufacturing device to solve that problem. And we recognize that as a company, but again, we feel like we fill a lot of those gaps and have lots of solutions for it. So.
Okay. Chris, I believe you touched on this a bit in the presentation, but one viewer would like to know, doesn't orientation matter when printing curved parts?
Yeah, and that is actually true. I said it earlier that orientation doesn't matter, meaning that we don't have to worry about fixturing, because fixturing happens as we build a part. But the viewer is exactly correct. Orientation does affect part resolution for curved parts. There's a stair-stepping effect. I will say, though, that the Objet process in particular, which has layer thicknesses down to 16 microns, we found that the orientation doesn't quite affect that as much as in other processes. On the FDM process, however, orientation definitely matters, as it has a larger layer thickness for surface quality. Yep.
Okay. Bruce, the next question comes from Paul. Are the separate polymer materials bonded?
Yeah, that's actually a great question. They are. Again, as I referenced before, the technology allows us to place voxels one next to each other. And the way the actual printing technology works is it actually layers down, as Chris referenced, a 16-micron layer. So the heads come over and it layers down a layer of 16 microns, and that layer is cured to 70%. The next layer that comes through, your first layer is now cured to 90%, and your second layer is cured to 70%. And because they're not fully cured, they bond together in the z-axis. On the third pass, your first layer is now cured to 100%, your second layer is cured to 90%, and your third layer is cured to 70%. So it's as strong in the XY axis as it is in the z-axis.
And I'll actually comment on that. We've done some tensile specimens of mixed materials and actually fatigued specimens of mixed materials, and I have to admit, we were surprised to find that it does not fail to bond. It actually does fail in the weak materials. So it fails where it's supposed to, and not at that interface, which is actually sort of surprising. We were pleasantly surprised by that.
Is there any difference in the structural integrity between the 3D printing and machined parts?
Sure, I can answer that. And the answer is, yeah, it is. Again, that's something that we've seen in the literature, and especially in the polymers. Again, different technologies are better at it than others. The most common reason is these interlayer bonding in the Z direction. So as we're, these layers could in tension peel apart or delaminate. So there is some weaknesses there. Again, that can be compensated through design, and again, there are some other processes that exist that perhaps have somewhat more equivalent properties.
Okay. And the next question, what surface finish is possible in plastic parts and also in metal parts without extra finishing operations?
David, could you repeat that question again? I'm sorry.
Sure. It is what surface finish is possible with the plastic parts? And then the follow-up question is, in metal parts without extra finishing operations.
Okay. So there's with PolyJet, I will tell you there's two different finishes. There's a glossy finish and a matte finish. So depending on which one of those you choose, you're going to get a different result. And again, as we referenced before, a 16-micron layer printing capability, when you're printing a curved surface with a PolyJet technology, you get very, very smooth surfaces. So it's a little tough to quantify. With FDM, the layer thickness is a little bit thicker, so you're not going to get as smooth surfaces. So it's tough to quantify from the point of view of, what is the ultimate capabilities, but I can tell you that there are plenty of people that actually use, and Chris referenced it in his presentation, where they use parts printed off a PolyJet machine for patterns in a molding situation, both in manufactured parts, as well as folks that have actually used FDM parts in a real production environment. So it really depends on what your needs are. Chris, I don't know if you have things you want to add to that.
No, yeah, we've done surface finish and the measurements as well. They're they're sort of in the 0.3. RA is like a 0.3 micron for glossy without any kind of polishing. Obviously, with polishing, it goes a lot lower. As far as metals go, we typically say it's sort of like a sand cast kind of. It does start with a loose packed powder, so it does have a powdered-like surface finish at the end. Those tend to require machining and finishing afterwards for the metal parts.
Okay. And Chris, the next question is posed to you. Does your lab use 3D CAD scanners? It looks like that may have been what was used for the bat ears.
Yeah, sure. So we, actually for the bat ears, they were actually using a micro CT. So that's actually, like a CAT scan, but just for small animal specimens. We do have laser-based scanning in the lab that we use, both handheld and desktop, and we also have the larger, point-based scanning as well. So yes, we do use that. And again, we tend to use that mainly for our design work, or reverse engineering work.
Okay. And do your students expect the companies that they work for after graduation to have 3D printing capabilities, or have any of them actually been sort of technology evangelizers for some of the companies?
No, I love this question, actually. Yeah, so obviously, I guess a goal of mine as an educator in this realm is for my students to go to their companies and say, hey, where's our 3D printer? I can't get work done here without it. So yes, my students do go into companies expecting them. At Virginia Tech, we have such a good collection, and we also have even a 3D printing vending machine that we've created so that every student at Virginia Tech has free open access to printing, because we do really feel like it's an imperative piece of being a good designer, being able to quickly prototype and bring an idea off the paper or off the computer screen into their hands. So yeah, my students do tend, I hope that doesn't, hopefully that people don't afraid to hire them, because that means they're going to have to pay some, more money to get a new machine. But no, to us it's imperative to design. So.
Okay. And could you share some of the cost metrics for some of the examples that you gave during the presentation?
Yeah, that's a good question. Basically, I would say for both the objet and the FDM material, we estimate, and I'm sure Bruce can give us a better number, something on the order of like $4 to $4.50 per cubic inch is usually what we estimate for a part.
Right. Yeah, that's actually aggressive. It's usually $5 to $6 is what we quote, and again, people don't like this answer, but it's really geometry dependent, right? Typically, with us or any of our competitors, you always have support material and you have model material. The model material tends to be a little bit more expensive than the support material. So if you have a design or a geometry that's more model than it is support, cost of the model might be more, and vice versa. But so we quote somewhere in the $5 to $6 range.
Okay. The next question comes from Matt. Are FDM and PolyJet capable of being watertight?
Yeah, Bruce, I'll let you answer that one.
Well, again, the layer thickness and how it's developed, the actual PolyJet parts, the way they're cleaned, they're actually used in, you actually clean them in something called a water jet. So you actually put the parts to remove the support material into a water jet to clean the parts. It does absorb a little bit of the water, but over the course of a little bit of time, that water is evaporated. We have lots of companies that are using the oil and gas industry that use it for testing of pipes and fixtures and things along those lines. So depending on your application, you can use it in that. I mean, you could build a box that is watertight. It will, depending on once it's fully cured, it won't absorb a ton of water. It will absorb a little bit, just like any plastic would. But depending on your application, again, like I said, the oil and the gas industry, it's used quite a bit for testing of pipes and fixtures and things along those lines. Chris, I'm not sure if you've
I think that's
the applications, but go ahead.
No, that's fair, and I would say that the FDM material is not watertight, but actually that's on that intake manifold example that we showed where we did the carbon fiber layup, we actually used that to our advantage, where we knew it was slightly porous, and so actually we knew that would give an opportunity to do some infiltration of a secondary material. So again, if you know what the technologies can and can't do, you can use those to your advantage when you design products.
Right. I will say that there's a case study on our site, Chris, for the University of New Orleans, where they actually did some robotics for an underwater snake. So they actually, in this video, you'll see that they actually put some mechanics inside a model and actually used it underwater to replicate how a snake would move inside water. So hope that answers the question.
Okay. Well, and we're at the hour mark now. One final question that came from Jordan, and Bruce, you can maybe answer this. How long do you think it will take before 3D printing gets to the point where it's as well made as, say, a dimension printer before $1,000 or $500 or less? Basically, a home printer that doesn't look like an erector set, but is still affordable.
That's a great question. I wish I could actually answer that question in earnest. I don't have insight, obviously, into R&D. It's funny. There are printers out there, as the question references, that you can buy for $1,000. But we tend to group our technology and the printers that we have in the professional 3D printing world. The others that are out there, we tend to lump into the hobbyist side of stuff. The fortunate thing is, there's 14 million CAD seats out there, and there's something on the order of 26,000 3D printers installed globally since 3D printing started. So there's plenty of room for advancement, and as technology advances and we install more and we advance the technologies, the price points will come down. Exactly when it's at $1,000 for a professional 3D printer, I wish I could answer that question, but I can't. The other thing I will add to that, David, is there's lots of folks I know probably, that are thinking about price points. Our Mojo printer is $10,000, so it's come down quite a bit, even from four years ago, where a dimension was somewhere on the order of $35,000 to $40,000. So you're getting a professional 3D printer right now for $10,000. And the last point, and then I'll flip it back to you because I know you need to wrap up, is there are lots of folks out there that understand the value of a part, and they're outsourcing right now. And sometimes they may spend $2,000, $3,000, $4,000 in a year on parts, so it's tough to justify that $10,000 price point. I can tell you almost 100% of the customers that we have that bring a 3D printer into their environment not only deliver their products faster to market, so they save time to market and sell their products faster, but they also improve their designs tenfold during the design process. So how you quantify that is often difficult. So sometimes people just try to look at it as a dollar-to-dollar match, and that's not always the right thing to do. I think there's other advantages to additive manufacturing and 3D printing that people need to consider.
All right, and with that, I'd like to thank Bruce Bradshaw and Dr. Christopher Williams. Thank you all for joining us. This has been Creating the Next Generation of Designers and Manufacturers with Additive Manufacturing. Thank you.